I'm a professor of astronomy at the Institute for Astronomy, University of Hawaii. I'm part of the university outreach program, and as part of that, a couple of times every year, I go around to libraries and talk about some of the hot topics of research and some of the hot topics of my own research and how it connects to the community and talk about that. The first time that I started this, I talked about aliens, finding planets around other stars and how that would contribute to our understanding of life elsewhere in the universe. And then when this year I was asked to do so, I said, well, we're living in mid of the ocean. Why don't I tell you guys where this water came from? But there are two questions before I start. So the topic of the talk is origin of Earth water. But the first question is, well, why is it important to know where the water came from? Right? So academically, we want to understand how Earth formed. We want to answer our curiosities: how Earth formed, what is the origin of its elements, how the mountains came about, how the oceans came about, how this is academically we want to know that. But beyond that, there is a lot of extension to that understanding, because by knowing where water came from, we can also understand how not only how Earth has water, how it maintains its water. Water is the birthplace of life, how life started there, and once we put all that together, how can we use this information to go beyond solar system, to go around other stars to see if other stars have habitable planets. Once we learn about these characteristics of our own planet, then collectively we can apply that to other planetary systems. More importantly, to figure out what to look for. You know, you want to look for a habitable planet, you got to figure out what to look for. And I will show it to you here. The best indication or the best signature that the planet outside in solar system may be habitable is if we can find signs of water molecules in its atmosphere. So there's a lot of implication to where this goes and how important it is to know the water. But the question is, why am I asking this question? Why am I asking that where the water came from? So Earth formed and water was there. Actually, it wasn't like that. Earth is supposed to be bone dry. And in a minute, I'll tell you why that is. Whatever Earth started with, that seed that grew and became Earth, was bone dry. And it was in the region of the solar system that everything else is bone dry. So how come Earth has water? How come Earth has water on its surface? And how come it can maintain the water, right? So everything goes back to our solar system. What you see here is an artistic rendering of our solar system with sun being right there at the center, and then you have the four small planets. Mercury is here, and you have Venus, Earth, the Moon, and Mars. And then you have giant planets sitting back there. This is Jupiter, this is Saturn, and this is Neptune, and the rest is back there. Now, what I want to draw your attention to is that region between Mars and Jupiter. That region is called asteroid belt. It's a region that there are no planets in there. It is populated by a bunch of objects, some of them as small as this, the tables and chair, and some of them as big as the island of Oahu, a big island. They are huge, huge pieces of rock going around there. And why this belt exists is much too scientific to fit into this talk, but what I want you to know is that there is this belt of stuff there. There is no planet in this region. There's this belt of stuff in there, and this stuff is stuff like this, and they are irregular. They are some of them are tiny, 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 like that one back there. Some of them are really, really big. You see, some of them are very tiny. Some of them are very big. Some of them have 326 miles radius. So we're talking about a bunch of material there, right? We can study this material. This is a top view of what I just showed you, except that this is not a cartoon. This comes right out of our observation of asteroids. There is a part of NASA at NASA JPL that traces and tracks every single asteroid. By the way, just so you know, a large majority of the asteroids have been discovered here by a couple of our faculty at the Institute for Astronomy using the old telescopes on Mauna Kea. So when you go to that website at JPL, and they keep track of all 750,000 asteroids, and then you say that today at 3 in the afternoon, give me a snapshot of where they are. And it produces that. So this is not actual asteroids. This is the position of the asteroid, put a dot there. At that specific time, when I said to the computer, give me a snapshot of the asteroids and all the planets, at that time, I don't remember the exact dates, but I got this myself. At that time, planets were exactly where they are. Jupiter was exactly there. These asteroids were exactly here. And it gives you that. Now, the reason I put this up there is the following. It is possible for us to study the characteristics and composition of these asteroids. They are like this. And during the formation of the solar system, these objects went around and they hit each other and they broke each other into pieces. Some of those pieces happen to come into our atmosphere, and you see them, the meteorite showers. Those are some of those pieces of fragments of the collisions among these big bodies. They happen to find their way into our atmosphere. When they get into the atmosphere, because of friction with the atmosphere, they become hot, they start shining, and they start burning. Some of them happen to fall on the ground. Some of them burn. Most of them burn in the atmosphere. They don't get on the ground. Some of them happen to fall on the ground. We call those meteorites. When they are in the atmosphere, when those fragments are in the atmosphere, they're burning, we call it meteor. Hence meteor shower. When they hit on the ground, if they hit on the ground, that little piece that hits on the ground, we call that a meteorite. Meteorites are tiny, tiny, tiny. This is, I was told that's a Canadian, this is a Canadian coin. There you go, it's a Canadian coin. And it was put next to this too, just to give you a scale of how tiny this stuff is, right? And you can find, if you know where to look, you can find them. For instance, if you find your way in North Pole, South Pole, if you're walking on ice and you see a piece of rock, that rock is a space rock. Because up there's only water and frozen water, right? There is no land there. So if you're walking on ice and you see a small piece of this little piece of rock, that has come from space, right? So there's actually a way to find this stuff. Then we take, so they're that little. We take them to our laboratory and we slice them and we put them under a microscope. And we study the characteristics of every single one of these things. And then we notice that some of them are dry. Some of them, when you look at the characteristic of the stuff that here, you can actually add some chemicals to it, and it tells you that this one has chlorine, this one has iodine, that one has that. So it tells you that stuff. We notice that basically many of them are dry. So let's go back here. We notice that majority of them that come from the inner part of this asteroid belt, they are bone dry, okay? So here is a question. If the stuff that is here is bone dry, it means that the stuff here receives so much heat from the sun that water cannot stay on it, evaporates and goes away. So if this stuff is dry, how come Earth is not dry? And that's the question. That is why we know that Earth, during its formation, it was bone dry. Something happened that water appeared on Earth, and hence the question. The reason that is a scientific question is that when you look at stuff beyond orbit of Earth, farther away from Sun, they're dry. Earth being closer than them, it should have been dry. It should have no water, right? So how come Earth has water? And that's the big question. If Earth formed in a dry environment, how come it has water? So to get to that, to answer that, and tell you about the implication. First, I have to tell you how Earth formed, and then I have to tell you where we think the water of Earth came from, and then the implication of it. So let's go through that. How Earth formed, or how a planet forms, how our solar system forms. There was Big Bang, and that bang produced a lot of gas and dust, and that gas and dust produced a lot of stars. Stars hit each other and coalesced and formed galaxies, and the universe has billion galaxies. Within each galaxy, you have billions of stars. The way that stars form is like this. Think of our Milky Way, a corner of Milky Way away from every other thing. You have a huge ball of gas and dust. And this ball of gas and dust is rotating because the whole universe is rotating. So this ball of gas and dust is rotating. But this stuff is so heavy that collapses under its own weight. So big and heavy that the gravity of the upper part pulls the lower part, the gravity of the lower part pulls the upper part. It collapses under its own weight. But as it collapses, if you have experience, if you take a tennis ball or racquetball and you squish it in your hand, it becomes warm. As it collapses, it warms up. The energy of the collapse goes to the gas molecules. These gas molecules, as they receive energy, as they become hot, they start moving around fast and they hit each other. As they hit each other, they produce more energy. There is more collapse, more energy, going around faster, hitting, going around faster, hitting, until that energy becomes so big that the next time they hit each other, there is nuclear reaction. Once nuclear reaction starts, that's where the star forms. A star is a huge ball of gas, hot gas with continuous nuclear reaction. So that's when the nuclear reaction forms. Now what happens is that nuclear reaction, it collapses, and then nuclear reaction forms the star at the center. Star shoots out a lot of radiation. That radiation goes up and down, it clears up everything, but leaves the center with the disk. So you have that cloud that is rotating, and as it's rotating, it collapses, the star forms, and then the star, along this direction of the laser, shoots out light, clears up all this area and energy here, and leaves you with that disk around it. So this is not something that I just made up. You can actually observe it. So, so what you see here is the dark band here is the star, is the disk that I just explained. Because the disk has a lot of dust in it, is blocking the light of the star. The star is in there. But the star shoots energy up and down. You can see that. It clears up and down, and leaves you with a disk. The same with here. The star is in there, you don't see it because the dust is covering its light, but it shoots up and down, clears up and down, and leaves you with a disk right there. And so that disk is where planets form. So now you have, let's go back here, now you have this disk. Now what I'm going to show you is that I'm going to turn this edge on and show you a cut through the disk. So first of all, this is a cartoon again. That's the disk that I just explained, a star form at the center. But what I want you to see is that in this cartoon, they made sure that the outer rim is dark because the dust doesn't let the light go out. It keeps it in there. Now, take a cut of this disk. The rest of the disk is coming out to you and going back in. So take a cut. The disk not only has all this gas molecules in it, it also has dust particles in it. And these dust particles are made of same stuff as the dust particle on our desk, except that they are about 1,000 times, 10,000 times smaller. And these dust particles do something very interesting. I'm going to explain that in the next slide. But before that, this is the cutoff. It has a lot of objects in it. But also, I want to show you what happens when you go away in the same disk, when you go away from your star is over there. If you are close to it, you receive a lot of radiation. As you go farther away, the radiation you receive, the heat you receive becomes less and less and less. If your object, if your dust particles has water molecule in it, if it is there, the water evaporates. They go farther, back, the amount of radiation becomes smaller and smaller, the heat becomes smaller and smaller. If the dust particle has water molecule here, there's a good chance it holds on to it. So when you go far away from the source of the heat, your disk, the same disk that has this dust objects in it, may also be able to hold on to water. The closer you come to the source of the heat, if there is any water, evaporates. That's why we are wondering if Earth formed there, how come it has water, right? Keep this in mind. I'll get back to this a couple of times. This is very important. The farther you go, you have ice. The closer you come, you don't have ice. You have rock. You have bone dry rock. Okay, so how do these objects, how do planets form? So go back to the disk. There are these dust particles. The dust particles and the gas, they're all rotating around sun. But the dust particles gently come close to each other. Because they are inside the gas, they are heavily coupled to the gas. The gas moves them around. So as they are moving with the gas, they gently come and sit next to each other. And when they are very close to each other, the molecules of this one and molecules of that one attract each other. They stick to one another. And this is very gentle hitting and sticking. And then this goes around and sits next to another one and next to another one. And that way, starting from one dust, this is a cartoon, that is reality. So start from dust particles, you get a little bit, they just sit next to each other and they form strands like that. You can actually reproduce that in laboratory by putting dust in some liquid, like paraffin or something. And then you let it rotate and dust particles make strands like that. Now, as they become that big, they show their motion, the independence from the gas more and more. As dust particles grow, become bigger and bigger, they care less and less about gas. In other words, they don't let gas push them more. They show their own independent motion. So when they were only two single dust particles, they were very gently coming next to each other. Now that they are bigger, they move a little bit faster. They show their independent motion. So they move a little bit faster. Now just imagine you have a bunch of these strands and they move faster and they hit each other. As they go through each other, sometimes they combine. Depending on how they hit each other, they may actually roll each other, they may actually shatter each other. Variety of things happen, but this happens so often that eventually, sometimes they hit each other, sometimes they merge, sometimes they roll. And this is again the same thing. Now you're in the same experiment, you allow these strands going around and hit each other, and they stick to each other. Sometimes they maintain the original form, sometimes they form big aggregates. This process continues until they start rolling each other, till you end up with the small little sands, the same sands of the size you see in the beach, the small little sands, right? Now your disk not only has dust in it, it also has sand in it. So sand goes around, these sand particles hit each other, some stick to each other, some shatter each other, some that just graze by each other. This process continues until you form bigger objects, boulder, the rocks, and then rocks go around, this whole process continues for about 500,000 years until you form objects as big as the moon and Mars. We call those, technical term for them is planetary embryos, because like embryo, they become planets, right? And then you have that disk that started with gas and dust. Now it has objects as big as moon, half a moon, as big as Mars, and objects like that. The asteroid that showed you 360 miles, and it has a variety of these things. And now this stuff is not coupled to gas anymore, because when object becomes 360 miles, it has a lot of gravity. When it attracts another object that is as big as, when object becomes as big as moon, it attracts smaller objects because it has its own gravity. So now these objects, they go around, now your disk has all this crap in it, they go around, and because they are big, they have gravity, they approach each other because of their own gravity, and they bang into each other, right? When they bang, some of them stick, some part of it sticks, some part of it goes away. We know how to simulate this. We know how to, we call this giant impacts. We know how to go to computer and say, take this stuff and bang them together and tell us what comes out of it. And what you see is a realization of those giant impacts. Some of the giant impacts erode a big body. Some of the giant impacts results into coalescence of objects and results into growth of the body into bigger parts. And that way, just by doing this, we know that how that giant impact resulted into objects gradually growing, right? So I said that I'm going to talk about this a few more times. Let's put that giant impact in the context of this, and let's focus on the fact that if you go farther out, you have more ice. If you go coming in, you have less ice, you have more rock. So here's the thing. You can try this when snow's on the Mauna Kea. Just go up there, make a snowball, and hit it to the wall of one of the observatories. It sticks, right? But just come down the same day. Come down, go to beach, and take two piece of rock and hit them to each other, or take a piece of rock and hit it to the wall, and it doesn't stick, right? It falls, right? So, what does it mean? The stuff that is back there is icy. When those collisions happen to them, they have a better chance of sticking together and growing faster, right? And so that stuff back there, those giant impacts results into rapid growth of bodies, and that's where Jupiter, Saturn, Neptune, Uranus form. They become big. That is why Jupiter is 320 times bigger than Earth. Saturn is 100 times bigger than Earth, because they form at a region where their seed was dominated by ice, and then collisions was just like throwing snowballs to a wall, stuck. But if you do that for the inner part is rock. Rock doesn't stick to rock. When you hit it to each other, they shatter each other into pieces. So what happens here into growth is that objects hit each other, they shatter each other into pieces, sometimes they stick, sometimes shatter each other into pieces, and then whatever is there goes around and sweeps off the fragments like a sponge and becomes a little bit bigger, and then something else hits it, takes some part of it away, it goes around and so this whole process of giant impacts, accreting, growing all this material, giant impact, breaking it up, continues until there is nothing left, right? And when there is nothing left, whatever is left is your planets. You know, there's nothing left to absorb, there's nothing left to sponge off. What is left is your planets. Except that when you're doing it up here, you can do it in a few million years. When you're doing it here, it will take several 100 million years. Giant planets, Jupiter and Saturn, form no more than 10 million years. Earth took about 100, 150 million years to form. Okay, I'll show you in a second. We go to our computers and we do the same thing on the computer. We say, we're going to put a bunch of those Moon to Mars size big objects next to each other, and then a bunch of those smaller ones, like the ones that are 20 miles, 360 miles, stuff, smaller ones, and a bunch of dust. These green ones that you see here, they are the ones that they're big as Mars, Moon. The blue ones are much, much smaller. This color coding here shows the mass in terms of mass of Earth. Earth is here. So anything that becomes red approaches mass of Earth. Anything that is around here, green, is about 5% mass of Earth. Anything that is here is about 0.1% mass of Earth. So then what we say to computer is that allow all these objects interact with each other through their own gravity. Allow this one attract that one attract this one, and let them hit. And then when they hit, that stuff that I showed you how the simulation, the original disk, if there is any water, is farther out here. So just by intuition, you would see if this is where objects can maintain their water, and this is where Earth forms, is it possible that after Earth formed, stuff from there came over here and delivered their water to Earth? Stuff back there that is icy, we call it comets. Those comets, these are ice balls, right? And dirty ice balls. So that stuff is cometary stuff. The question is it possible that comets from farther away, from region beyond Neptune, beyond Pluto, is it possible that comets from that region somehow found their way to this region, and then when they collided with Earth, they splashed their water all over the Earth, and that way water appeared on the surface? You would say yes, and it's not unlikely. There is just one little problem. So this is a cartoon of Earth crust, Earth ocean. You have the ocean on the top of the Earth, right? And this is a little bit of the mantle, and it goes down to about 1,000 miles or so. The problem is this. The water on the surface of the Earth is not the only water. There is about 20 times more in the mantle, and even more than that in the core. So if you want to bring the water with the stuff from here, smash it to Earth and cover the surface, you're not going to be able to explain why there is more water in the mantle and there is more in the core. Because there is more water in the mantle and the core, the water on Earth must have come to it during its formation. As it was forming, it must have, as it was sponging all this stuff, it must have attracted a lot of objects that had water in them. Now, by water, I don't mean liquid water like water you get from faucet. What I mean is water molecules inside the rocks, inside those pebbles, inside those dust. That stuff, when it becomes a lot, I will explain to you, when it becomes a lot, it actually produces ocean. But when it comes to Earth, it doesn't come in terms of liquid. It comes as molecules inside rock. right? Okay, so where does it come from? So let's go back again to this. I mentioned to you that when we studied this part, we noticed that they are all dry and everything. But when we extend our studies to farther away, we see something interesting. We see that the stuff that is here and the material that comes from here, asteroids that are here, or meteorites that come from this region, they actually carry water. So this is one of them. This is an asteroids series that was visited by NASA's Dawn spacecraft. And the spacecraft found something very interesting, that little thing out there. Now, if I zoom on it, that little thing happened to be subsurface water. So that is, something hit that asteroid, and that asteroid got a dent over there. The subsurface water exposed, and the ice sublimated went away, the salt stayed. And the salt reflects sunlight. So that the fact that there is this there means that there used to be water. It means that if you excavate there, same thing will happen. There will be water in there. If you excavate right here, there will be water. Again, it's not ocean water. It is the water is H2O molecules that are inside the rock. Okay. So this is one of the indications. The other indication comes from a new mission that was by our Japanese colleague. Is called Hayabusa mission. Hayabusa mission was launched in 2014, went to this asteroid. This asteroid is called the Ryugu asteroid. It went to this asteroid, and the purpose of it was to hit the asteroid, grab some material, and bring back. And that is the actual thing happening. The spacecraft goes down, hits the asteroid, grabs some, hits the asteroid, grabs some, and comes back and brings back to Earth. So it brought things back to Earth last December, and this is the stuff. This is the scale of 5 millimeters. This from here to there is less than an inch, is about 2 centimeters. It's less than an inch. And this whole material is about 5 grams. It's tiny, tiny, tiny. This has been studied, and it was shown in the laboratory that it is hydrated. Some of the grains there have some indication that they carried water molecule in them, right? So what does that mean? Let's go back here. Stuff from here happened to be dry. Stuff from here happened to have some water in them. Doesn't have to be really wet. It has some water in them. So now let's go do that simulation that I did here for you. Oh yeah, that simulation that I did here for you. Now what I'm going to do is that I'm going to do exact same thing, except that I'm going to take stuff here to be dry. I'm going to take stuff to have a little bit of water, stuff here to have a little bit less water. So let's do this. Let's go ahead and take that. Now it's the exact same thing. Sun is here, Jupiter, Saturn are over there, exact same thing. Now what you see down here is the amount of water. Red means basically no water, 1 millionth of volume of mass. This means 10% of the mass. So dry, a little bit of water, and a little bit more water. Earth is about this part. So look at this, 0.001 means 0.1%. Earth is 99.99% rock, is only 0.1% water. That ocean and 20 of it in mantle and more of it in core is only 0.1% of mass of Earth, right? And we want to explain that. Okay, so keep that in mind. So I'm going to do exact same thing that I did before. You're familiar, these objects, these things, they're going to hit each other, and it's going to pick up the whole thing, and soon you will see that how Earth forms. And now what I want you to see is that in the previous one, I said pay attention to change of colors. The red one is Earth. Now pay attention to change of color. Anything that becomes blue is gaining water, right? Anything here that becomes blue is gaining water. You see that? Anything that in this region became blue is gaining water. So now you have 3 planets similar to our solar system. They all started dry, but look at their color is around this part. It's about 0.1 to 0.5. It's about 0.1 to 0.5% water. Where did water come from? It came from the stuff in the back of the asteroid belt. The same asteroid belt, that front of it was dry, back of it has a tiny, tiny amount of water. So what happens is that, this is what happens. What happens is that this asteroids, the one that has a little bit of water hit the one that doesn't have water, and then passes its water to it. And that one hits another one that doesn't have water, passes a little bit more water to it. And this continues until the water, not the asteroid, the water gets transported to the zone that Earth forms, and Earth sponges that off, right? That way you can explain that the water is inside of Earth, is not just on the surface of it, right? So these asteroids that I explained, this is going to run. So an asteroid from farther back that has water hits an asteroid that has less water and transferred water to it. Look up here when it runs again. So an asteroid that has more water, the asteroid that has more water hits the one that has less water, okay, and that transfers some of these waters to it, carries some of the water itself. After it's gone, this one hits another one, transfers some of that blue one. This one hits another one, transfers some of that blue one. This blue colors, the waters, get transferred from one collision to another, to another, to another, and that way find their way to where Earth is. And as Earth is growing, it grows that leftover material. It grows by sweeping that leftover material. That leftover material has water in it. Water goes inside of it. It grows a little bit more, attracts more, water goes inside more, and that way you put water inside Earth. Earth forms with the water inside. Again, this is not liquid water. This is water molecule inside the rocks, inside Earth, okay? Okay, so these are another type of collisions. Variety of different objects come in, variety of different collision angles. They hit each other. Some of them go away from each other. Some of them transfer the entire water to one another. So variety of different things happen. They merge. They go away from each other. This process continues several 100 million years until you have the planet and the water is inside of it. Okay, so I showed you how Earth forms, and I explained where the source of its water comes from outer asteroid belts, and then I showed you that when it forms, the water ends up inside of it. But how does it come outside, right? So you form it, it is inside. The rocks have water molecules in them, but how did water come outside on the surface? So how did water appear on the Earth's surface? Well, when all these collisions happen and Earth is forming, Earth is molten. You know, every collision carries a lot of energy and it's like a huge bomb. When it hits something, there's all this energy that goes around and melts the whole impactor. So you have Earth that is forming, is growing, and is really, really hot. And the way that it cools down is the way that lava cools down. When lava cools down, the heat from inside opens up the surface, right? And stuff comes out, right? So the surface of Earth, as the surface cools down, the molten lava from the bottom breaks the surface into plates. Those are plates that later on become continents, right? It breaks it into plates. And as plates open up, the gap between them, from the gap between them, gases come out. These gases are from inside, the same place where those water molecules were. They come out, right? Let me see what I have after that. Okay, so they come out, and as they come out, they go up, 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 they cool down. The water molecules that inside Earth was in form of steam, it comes up and goes up there, it cools down, it becomes liquid. It rains back. As it rains back, it cools down the surface, but the bottom, inside, is still molten. Opens up the surface again, and this process continues, right? It continues, it forms the atmosphere of Earth, and that atmosphere continues participating until the surface saturates and the water stays. And that process takes several million years until so the water stays on the surface because the surface got saturated, but there is more water inside, right? Now that explains our atmosphere. That explains where water came from, and explains why water stays on the surface. There's still one last question. So if that's what it is, after a while, with all the heat that we get from sun, the water should evaporate and go away, right? You see that with the small lakes. If there is no sustaining of the water of a lake, it evaporates, right? So this stuff should evaporate and go away. and as it happened to Mars, for instance. So why is it that Earth maintains it? That comes to the way that continents work and the way that continents move. It comes to plate tectonics. So Earth the surface breaks into plates, and the plates are moving on this lava, and the underneath is hot and molten, okay? What happens underneath is the following. Underneath is hot and molten. The molten stuff melts stuff that the already cooled layer on the top melts it and find its way out. Most of this happens inside at the bottom of the ocean. As it finds its way out, it comes out, it opens these two regions away from each other, okay? Like this. It opens the way, you see the rotation, it opens the way up, and it moves the two pieces of the bottom of the ocean away from each other. Now, if one of these that gets pushed away happen to be one of those plates in the vicinity of the other one, right? They go on top of each other. One goes underneath, one goes on top. If there is, because of the weight, when it gets pushed away, because of its weight, this plate is heavier, goes down, that plate is lighter, come up, right? It goes down, it gets to the hot part, it gets molten, comes up, and in form of volcanoes. The same thing that went in comes back up in terms of volcanoes and spews a lot of gas in the atmosphere, right? The biggest and the most important of those gases is CO2, global warming, right? That CO2, that's why the global warming makes sense, because that CO2 comes out and covers the entire Earth in form of a blanket, right? Because this cycle continues, that blanket maintains the temperature of surface of the Earth. Regardless of what we get from sun, it maintains the surface of the Earth at a uniform temperature. A uniform temperature that allows water to stay in liquid form. And anything that goes up comes back down again and then comes out through the volcanoes, right? If this CO2 becomes too thick, then it actually is like you put too many blankets on you. It makes the underneath of it much warmer. If it becomes too thin, then underneath becomes cold and the stuff goes away. Earth happens to have the right amount of CO2 to protect it as a blanket and to maintain uniform temperature. It is true that the temperature here is about 80 degrees and then you go to North and South Pole at the same time there is ice and everything. But in general, if you take the average temperature of the surface of Earth, it is uniform throughout. It changes by about a fraction of a degree every year, but is uniform. And that is enough to maintain liquid water on the surface. Okay. And because of that, when life appeared in water and found its way to the surface and stayed, it managed to stay. Life started in water and then found its way to the surface of Earth, but it depends heavily on water. Because water stays on the surface, life found its way to maintain itself on the surface of Earth. And that we use that concept that I explained to you to define a to assign a technical term to it. We call it habitable zone. The habitable zone, you have heard that in news, they say Goldilocks region and habitable zone and all that. It means that Earth is at the place from sun that the amount of the CO2 that it generates itself is enough to maintain the temperature so the water stays in liquid form. And once the water stays in liquid form, life can maintain itself. So I hope that I was able to convey to you where water comes from, why Earth should not have water, but now it has water, and how it maintains its water, and what its implications are. And the next step that we have been doing, actually using telescopes in Mauna Kea, we use this concept and look into stars that show signs of having planets like this. If you are interested, I can show you a few slides of that as well. Having planets like this that could potentially be habitable. And the next step would be to put this JWST, the new telescope, towards those candidate planets to see if they have water molecule in the atmosphere. If they have water molecule in the atmosphere, it means that there is water on the problem. Most likely there is water on the surface that is constantly going to atmosphere, rain back, right? If there is water, there could be life. It's not 100%, but it's one of the essential elements of it. Thanks so much.